When you're running a thermal power plant, efficiency is everything. I mean, every single fraction of a percent counts. Today, we're diving into a really critical piece of equipment that's all about recycling energy that would otherwise just go up in smoke. We're talking about the air preheater, or as you'll hear it called, the APH.
So here's our game plan. We'll start with the basics, what the APH is and what it does. Then we'll get into the nitty-gritty of the heat exchange process. After that, we'll look at the main types of systems you'll find out there, crunch the numbers on the efficiency equation, and wrap up with all the key operational perks they bring to the table.
All right, first things first. From an engineer's point of view, what is an air preheater? And maybe more importantly, where exactly does it live inside the maze of a modern power plant's air and gas systems?
At its heart, it's a heat recovery machine. Think of it like this. Its whole job is to grab the thermal energy from the hot exhaust gases, heat that would normally be totally wasted up the stack, and pump it right back into the system to improve the whole unit's performance.
Now, its location is absolutely critical. You'll find the APH sitting after the boiler's economizer, which is busy preheating feed water, but before the electrostatic precipitator, or ESP, which cleans up the exhaust. This spot makes it the last major stop for heat recovery before the emissions equipment takes over. Okay, so let's get into the core engineering here. We're going to visualize how all that thermal energy actually moves from the hot exhaust stream over to the cold air coming in. The process itself is pretty elegant. You've got hot flue gas, we're talking around 230 degrees Celsius, coming in one side. On the other, you're pulling in cool ambient air, maybe around 40 degrees. The two streams flow past each other, separated by a metal surface, and the heat naturally moves from the hot gas to the cold air. The key thing to remember is they never actually mix. So what you get is nice hot air heading to the furnace and much cooler flue gas going out the stack. Now this is a fantastic engineering rule of thumb that really governs how these things perform. For every 2-degree drop you get in the flue gas temperature, the combustion air heats up by about 1 degree. That ratio is fundamental to designing and sizing these units. But, and this is a big but, you can't just keep cooling the flue gas forever. There's a hard limit. 140 degrees Celsius is what's known as the acid dew point. If you let the gas temperature drop below that, the sulfur in the gas mixes with water vapor and forms sulfuric acid, and that stuff is incredibly corrosive. It will literally eat away at your downstream equipment. Okay, so we get the process now. Let's look at the two main ways engineers have actually designed these systems to work on a massive industrial scale.
The two big designs really come down to mechanics. First, you have the recuperative type. It's static, no moving parts. Think of it like a giant radiator where the air and gas streams are always kept separate by plates or tubes. Then you have the regenerative type. This one's a rotary design where a huge wheel packed with heat-absorbing material literally spins through the hot gas stream, soaks up the heat, and then rotates into the cold air stream to release it. Now, the regenerative ones are usually more efficient and compact, but their big challenge is preventing leakage between the two streams right at the seals.
And this right here is where the air preheater really proves its worth. Let's put some numbers to it and see the direct impact it has on the single most important metric, overall boiler efficiency. The whole efficiency gain is built around a really fundamental rule of thumb, and it all starts with this one number. And here's the rule. For every 20 degrees Celsius jump you get in the combustion air temperature, the boiler's overall efficiency goes up by about 1%. Now, 1% might not sound like much, but in the power generation world, that is a huge engineering win. It adds up to massive fuel savings over the life of a plant.
So what does that look like in the real world? Let's say we manage to get a 120-degree temperature rise in our air. Well, the impact is pretty dramatic.
A 120-degree rise in that air temperature gives you a direct 6% increase in your overall boiler efficiency. That is a massive improvement no matter how you slice it. We're talking about major savings on fuel costs and lower emissions for years and years.
But hold on, it gets even better. The benefits don't stop with that one big efficiency number. Preheating the combustion air creates this whole cascade of other positive effects that you feel throughout the entire boiler operation. Yeah. The benefits just keep stacking up. Hotter air means a more stable, more complete combustion. That means you can get away with using cheaper, lower-grade fuels. You also burn more of the fuel, so you get less unburnt carbon in the ash. It raises the furnace temperature, and for coal plants, it's a huge help in drying the pulverized fuel right before it's burned. It's just a win-win-win.
So, you can see the air preheater is just a perfect example of turning waste heat into real value. And this whole principle kind of forces us to ask a bigger question, right? What other sources of waste heat are just sitting there inside a power plant cycle? And how can we, as engineers, figure out ways to capture that energy and put it back to work?